So in this video of chapter number 10 circles, we're going to see an interesting concept, and that is called perpendicular from the center to chord. Okay, so what we're going to do is we're going to draw a circle first of all. So let's say this is our circle. Then we need a center and we need a chord. So every circle has a center. So let's just say this is our center O. Okay, then we want to have a chord. So what is chord? Chord is nothing but take any two random points P and Q on the circle and draw a line connecting these two random points on the circle. So this is our line PQ, and this line segment PQ is called as the chord of the circle, as we have seen in the previous videos the definitions of chord of a circle. Now once we have a center of a circle and we have a chord of a circle, what we are going to do is we are going to draw a perpendicular line, okay, from the center to the chord. So let's do it. Let's draw a perpendicular line from the center to the chord. So this is my, okay, so this is the perpendicular line from the center to the chord, and I'm going to mark it like this because it's a perpendicular. Okay, so we have constructed a perpendicular from the center to the chord. Now this is one chord that we have seen in this circle. Similarly, there can be another chord. So I'm just going to mark another chord here. So let's say this is my another chord. Okay, let's make a straight line. So this is my another chord, and let's call it X and Y. So X and Y. Now, can we draw a perpendicular from center to this chord? Yes, obviously. So let's try to zoom in a bit. Yes. So this will be the another perpendicular that we draw from the center towards the chord. Okay, and I'm going to mark it like this. Okay, let's mark it like this. Yes. So this is another perpendicular from the center to the chord. Similarly, we can have multiple chords in different directions, in different orientations throughout this circle, and we can always construct a perpendicular from the center to this chord. Now, why are we exactly doing this? Why are we constructing these perpendiculars to the from the center towards the chord? The reason is that this perpendicular that we draw to the chord has one very interesting property that is we are going to see in the next theorem. So here we already have this figure, okay, where we have one perpendicular from the center to the chord. Okay, now let's see what the theorem says. So I'm going to remove this, okay, and try to zoom in a bit. Yes. Now let's read the statement. The perpendicular from the center of a circle, so this is center of a circle, to a chord, so this is to the chord PQ, bisects the chord. So I'm going to highlight this keyword, bisects the chord. Okay, that is an interesting property of a perpendicular which you draw from center towards the chord. So if you see this above figure, so this will bisect the chord at this point. So we forgot to mention the points. Let's say this point is A. So it will bisect the chord at the point A, which means that A will be the midpoint of this chord PQ. Similarly, if you look at this, and let's call this as B, let's call this point as B. So again, this perpendicular OB will bisect the chord XY, which means that, yes, which means that XB will be equal to BY. B will be the midpoint of the chord. In fact, let me put 3 lines here because we already have 2 lines here. Okay, so that is what is the property of this perpendicular from the center to a chord. It bisects the chord, which means point A will be the midpoint of this chord. Now once again, since this is a theorem, we have to prove this theorem. So in order to prove this theorem, step number 1, so let's use, okay, step number 1 will be construction. So construct, okay, radius, construct radius OP and OQ. Okay, so I'm going to do that construction. Okay, let's use a different color. Let's zoom in. So this is a construction OP, okay, and OQ. Now we all know that OP and OQ are the radius of the circuses, radius of the circle. So very obviously, okay, OP is equal to OQ because they are the radius of the circle. Okay, now focus on this two triangles. Okay, let me highlight it. Focus on this triangle OPA, okay, and this triangle OQA. These are the two triangles in this circle. If you note that this triangle, these two triangles are the right angle triangle. Okay, why? Because this is 90 degree, it's given to us, and this becomes the hypotenuse. So both the hypotenuse of the triangles are equal to each other, plus there is this common side OA to both these triangles. In other words, we can use a RHS test of congruency, right angle hypotenuse side test of congruency, to prove that OPA is equal to OQA. And once we prove the congruency of triangle, then we can say AP is equal to AQ, because they are corresponding parts of congruent triangles. And then we can say A is the midpoint of this chord PQ. So that is how this theorem is going to proceed. Let's start noting down the points. So first thing we have done is we have constructed the radius OP and OQ. Okay. Now, so point number 2, let's use same color. Okay. Point number 2, consider, okay, consider triangle OPA and triangle OQA. So the highlighted green triangles. Okay. So in that, the first thing is angle A is equal to 90 degree. Okay. Therefore, both triangles are right angle triangles. Okay, that's an important point. Right angled triangles. Okay, that is the first point. Then the second point is hypotenuse OP is equal to hypotenuse OQ. Okay, why is it? Because they are the radius of the circle. So I'm just going to write a radius of same circle. They are the radius of the same circle. So they are going to be equal to each other. And the last point is OA is equal to OA. Okay, why? Because it's the same side. So it's obviously going to be equal to each other. Okay. Now, once again, quickly to revise, in this triangle, so I'm going to use a highlighter. In this triangle OPA and OQA, we have noted down three properties of these two triangles. One is that it's a right angle triangle. Second is that the hypotenuse is equal to each other. And third is that the side is equal to each other. And thus, from these points, we can conclude. So I'm going to come here. So point number 3. Thus, by RHS, which is right angle hypotenuse side test of congruency, okay, we can say that the two triangles are congruent to each other. So triangle OPA is congruent to triangle OQA. Okay, and once we have proven that these two triangles are congruent, then we can say that this PA is equal to QA. Okay, that is, I'm going to use a different color. That is, PA is equal to QA. Okay, why is it so? Because they are corresponding parts of congruent triangles. CPCT is a short form for corresponding parts of congruent triangles. That is, if PA is equal to QA, that is, A is the midpoint. A is the midpoint, okay, of PQ, of the side PQ, and that is OA. We say OA bisects, okay, OA bisects side PQ. So all these three different statements are basically the same thing which we are saying in different way using different words. Okay, PA is equal to QA, which means that A is a midpoint of PQ, which means that OA bisects the side PQ. So this OA, which was a perpendicular drawn from the center to the chord PQ, has bisected the chord PQ. So let me try to get rid of this highlighted things. Yes, so that is clear. So thus, this theorem that we wanted to prove has been proven, that the perpendicular from the center of the circle, this is the center of the circle, to a chord, to this chord, has bisected the chord. Okay. Once again, this chord could be anywhere. As we have seen this chord could be here. So if you draw perpendicular, this will also bisect the chord. Chord could be here, chord could be here. It could be any chord, anywhere, it will get bisected. So this was an interesting theorem about the perpendicular to a chord. Now we also have a converse of this theorem. So the converse of this theorem is here. Okay, we have overwritten. Okay, let's try to move this. Yes, this is the converse of the theorem. Let's try to get it down. Okay, let's read what the statement says. The converse reads that the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Okay, so once again This was the figure that we are going to refer. Okay, let me take it down. Okay. Okay, let's try to. Yes, good. Okay, so let's try to read the theorem again. Here in this figure, we have a line drawn through the center of the circle. So this is the center of the circle to bisect a chord. So we have constructed a line from center of the circle to the midpoint of the chord. So AP is equal to AQ is already given to us, and we have to prove that this is perpendicular to the chord. So let's note it down if it's not very clear. To prove OA is perpendicular to PQ. Okay, that is the thing that we have to prove. And what is given to us? Given that AP is equal to AQ. Okay, A is the midpoint of PQ, so this is given to us. AP is equal to AQ. Okay, so now once again the proof follows the very similar pattern that we saw in the original theorem. We have to construct this radius. So PO OQ, this radius is constructed. Okay, so since they are radius of the same circle, so we are going to say OP is equal to OQ. Okay, because they are radius of the same circle. Then we have AP is equal to AQ, that is given to us, and then we have OA is equal to OA, which because it's the same side of the two different triangles. So let's note it down. In triangle OPA and OQA, okay, first thing, OP is equal to OQ because they are same radius of same circle. Actually, they are not same radius. This is wrong. Radius of the same circle. So they are equal to each other. Then the second point is AP is equal to AQ. Why so? Because this is given. Okay. This is how the construction is done. Okay. This line is drawn through the center of the circle to bisect a chord. That is very important. That is how the line is drawn. It is a line connecting the center to the midpoint of the chord OA. So AP is equal to AQ becomes given. And then the third and the last point is point number C. OA is equal to OA because they are the same sides of different triangles. Okay, and thus by SSS test, side, by SSS test we say these two triangles are congruent to each other. So thus by side test of congruency we say triangle OPA is congruent to triangle OQA. Yes, and that is from this it follows that angle OAP is equal to angle OAQ. Why is this so? Because they are again corresponding parts of congruent triangles. So once we know that this angle, okay, so once we know that this angle is equal to this angle because corresponding parts of congruent triangles, then we know that these two angles, okay, this angle and this angle, let's try to zoom in, this angle and this angle, their summation is equal to 180 degree. Why so? Because it's a straight angles. That's a property of straight angles. So we have point number 4, but angle OAP plus angle OAQ is equal to 180 degree. Okay, why? Because these are straight angles. So we are short of space. Okay, but they are straight angles, but also they are equal to each other. Therefore 2 times of angle OAP is equal to 180 degree. Therefore angle OAP is equal to 180 divided by 2, that is equal to 90 degree. Okay, so this angle OAP, this angle is turned out to be 90 degree, and so is this angle. Both of these angles are equal to 90 degree, and thus we have shown that if we draw a line from the center of the circle to the midpoint of the chord, then it will always be a perpendicular line. So that is the converse of this theorem. Let's read it once again. A line drawn through the center of the circle, so this is the center of the circle, to bisect the chord, so it will bisect the chord, is perpendicular to the chord. This is what we wanted to prove, that it is perpendicular to the chord, and we have proven it using the test congruency of triangles. So the congruency triangle was SSS test. Using SSS test, we have proved this converse of the theorem. So both these theorems are very important. They are related to this concept of perpendicular drawn from the center of the circle. No matter what the chord is or what is the orientation of the chord, if you draw a perpendicular from the center of the circle, it will bisect the chord. So this property is very important, and we will be using it in different exercises that we will solve in our upcoming sessions.